So I'm Jensen. I'm a PhD student under Pierre Song in the Energy Analytics and Market Group. And I want to make the case that we have a fundamental problem. We, the collective we in the electricity market and systems research area, we have a fundamental problem that we don't have a good test case to actually check all the things we want to check. And I've put that in the title here as we're doing strong research, but we're doing strong research on weak data. If you look across the literature across the last 10 years or so, what you will often find is that when we have a new market proposal or we have a new proposal for anything that has to do with the system, we use, for instance, an IEEE test case or a very simplified network setup. So this is from a recent paper, and it represents, for instance, Belgium using just 2 nodes, when in reality the Belgian system has 35 or so high voltage transmission buses or high voltage buses in their network. And the reason this happens is that the data just isn't available. If you want to do this kind of research, you either use one of these test systems that are open or that you define yourself in a simplified manner, or you contact NSRI and you say, I want to use your STUM model. And they say, okay, please sign this piece of paper that says you're not going to share the data that we give to you and you're not allowed to discuss certain parts of it, and so on and so forth. So you sign a confidentiality undertaking, or you sign an NDA. And this is a huge problem because when people actually use this data and they show some nice results on it, it's impossible for the rest of us to check that they're actually doing the work they claim they're doing. And it's impossible for us to reproduce the results, unless we contact NSRI and we just so happen to get access to the same data, and that's a long and drawn-out process. And then other people can check us again. So I want to try to address this, and I want to try to address this by building a better test case for us. So if you think about what a test case actually is, in this case, it consists of 4 parts. There's a network, which when we discuss or when we want to do this kind of research, we want a very large-scale network. There's generators, a specification of where are the generators, what are the costs associated with the generators, and what is the power that we have available in them. There's a load signal, so there's demand across our network. Where is it located? How much is it in each time step? And we optimally, when we want to do renewable energy, we also want a specification of how much wind energy is available and how much solar energy is available. And we want forecasts for their production. So there's these four things we have to go through, and I'm going to talk about how I addressed each of these problems in order to try to build a better test case. So the first thing I did was to go out and look for a large-scale network. And it happens that there's one produced by Bialik and Huchion, which covers the main European area. This test case is so large that we're actually able to cover many different countries, different wind scenarios. We have good description on a reasonable resolution of the transmission grid, and where we have everything we need to build a good test case here. Except we don't have any information about the generators, and we don't have any information about the renewable energy or the load. So that's something that I had to go out and construct. For the generators, first of all, I found a database of generators. So there's about 1,000 generators here, built using open access again. So it's built by people who are able to find sources on the generators close to the places they live. And I then associated costs to these generators based on their fuel type and their capacity. So we have a simplified setup with all the generators, and we're able to give you the cost functions of all these generators. Now the tricky one is the renewable energy signal, because renewable or wind power generation is not available at the resolution or the scale that we would like here. A lot of data sources are simply missing. So what we do instead is that we turn to high-resolution atmospheric data from our colleagues, in this case at the German Weather Institute, who have very high-resolution data covered each hour for some number of years. We take the wind here, where the dark areas represent areas with a lot of wind, and we run them through a simple turbine model, where we say the more wind you have, the more electricity basically you're able to produce. So we have that on these maps, and if we aggregate that to the buses of the network, we're able to, for each bus, give you not only a measure of how much wind actually came in, but we're also able to give you forecast, because we have the forecast of all these wind and solar fields. So we're able to give you these forecasts over 3 years of data, and we're able to give you a forecast every 12 hours for the next 91 hours ahead. In the similar manner, we can treat the load as especially homogeneous and put it on the nodes as well. So we have all this, and if you combine these different sources, what we're now able to do is to show the impact of congestion on the entire European grid. If we assumed that we had nodal pricing in Europe, the entire European grid for all 3 years of data, we're able to analyze these prices and figure out where are the big congestion highways. Now, a dark color in this plot indicates that you have a higher electricity price. That means you're not using a lot of renewable energy. So we can see that probably the first place we should look here is at the interconnections with Italy that might be restricting how Italy is able to use renewable energy. But most importantly, because I've chosen the sources I have and the methods, and I've done most of this work myself, I'm able to make this available as a fully open access dataset. That means you can go in and you can get the dataset, you can share with your colleagues, and you're also able to look into my code that I used to generate it and check that I'm not doing any funny things with making some assumptions or using some tricks in order to build a dataset that there's no basis in. Thank you.